having learned about the Liebniz theorem, and after proving the theorem, we are now in a state to understand the relation between density function and different types of ensembles. In this lecture, we will distinguish between the density function for microcanonical as well as canonical ensembles. So we have seen that the density function represented by rho is in general a function of the phase space coordinates qp as well as time. And by Liebniz theorem, we have seen that the total time derivative of this density function d rho by dt must be equal to 0. And we have shown that d rho by dt can be expressed as dou rho by dou t, the partial derivative of the density function with the time, plus rho with h, the Poisson bracket, where h is the Hamiltonian of the system. Now, there are two terms in equation number 1 on the RHS. We can just analyze under what conditions these equations are giving us meaningful results. So, we have to remember that the condition dou rho by dou t is equal to 0, dou rho by dou t equal to 0 is the condition for equilibrium of a system. It is the condition for equilibrium of a system. We have defined a stationary ensemble which represents a system in equilibrium. So dou rho by dou t, so in what all ways d rho by dt can be equal to 0, that is what we are going to check it. Okay, so when d rho by dt equal to 0, it can happen when both dou rho by dou t as well as the Poisson bracket of rho with h are 0. So if dou rho by dou t equal to 0, it means that that is a condition for equilibrium of the system. Now, this condition need not be always satisfied. Why? Because a given system may be in a state of equilibrium, may not be in a state of equilibrium. So if the system is in a state of equilibrium, then only we can conclude that the term dou rho by dou t is equal to 0. That is the thing you have to keep in mind. But remember that Liebniz theorem demands that whether the system is in a state of equilibrium or not in a state of equilibrium, the total time derivative d rho by dt must be equal to 0. So when Liebniz theorem is derived, we do not state that, or we do not place the condition that the system is in equilibrium. We derive the Liebniz theorem for any system which is what maybe in equilibrium, may not be in equilibrium. So remember that this particular condition d rho by dt is a general condition which is true every time. So this is a condition true for all systems, whether the system is in equilibrium or not in equilibrium. So now we can say that under what condition simultaneously this particular equation and this particular condition, both the conditions are satisfied. So the condition for simultaneous validity, of d rho by dt equal to 0 and dou rho by dou t equal to 0 will be the Poisson bracket of rho with h must be equal to 0. I think it's crystal clear. Why? Because equation number 1 just gives that hint. So d rho by dt is always equal to 0, and if dou rho by dou t is also equal to 0, then certainly we can conclude from equation number 1 that the Poisson bracket of rho with h must be equal to 0. So what is the definition of Poisson bracket of rho with h? That is we can say sum over I, of course it is running from 1 to 3n, then dou rho by dou qi, I just expand it into dou h by dou pi minus dou rho by dou pi into dou h by dou qi. So it means that this term should be equal to 0. So that is we call it as equation number 2. Now the question is that under what condition equation number 2 will be holding correct? Under what condition equation number 2 will be satisfied? Okay, so we can say that equation number 2 can be satisfied in different ways. Okay, so equation 2 can be satisfied, equation 2 can be satisfied in different ways. It's not a unique way. In different ways equation number 2 can be satisfied. Okay, the Poisson bracket rho with h can be equal to 0. See, let's discuss one by one. The first case, we say that the first case is when rho is independent of the coordinates q and p, correct? That is, rho is independent of the coordinates q and p. Then certainly the Poisson bracket of rho with h will be equal to 0. You clearly understand that because, okay, what is the Poisson bracket rho with h? By expansion given by equation number 2, you can see that is dou rho by dou qi into dou h by dou pi minus dou rho by dou pi into dou h by dou qi. So if rho is not a function of q or p, what will happen? Automatically the term dou rho by dou qi will be equal to 0, and here dou rho by dou pi will be also equal to 0 if rho is not depending on q and p. So what is meant by rho not depending on q and p? It means that the value of density function is not changing from point to point in the phase space, because you know that q and p, okay, see, q and p are denoting a set of points in the phase space. So if the density function is not depending on q and p, it means that the density function is remaining a constant in a given region of the phase space. The density function does not show any variation, or all the representative points are distributed uniformly over the accessible region of the phase space. Then we can say rho is independent of q and p. So if rho is independent of q and p, we can say that the Poisson bracket of rho with h will be equal to 0. Okay, that is equal to 0. Now that is, I can say rho qp, which is in general rho qp is equal to c, say a constant. So the equation 2 can be satisfied when rho qp equal to c, a constant, over the relevant region of the phase space. Okay, over the relevant means accessible, over the relevant region of the phase space. I'm writing PS. Okay, and rho qp will be equal to 0 outside that region. That's, I can write elsewhere, outside the relevant region. So in this case we can say that the rho will be the Poisson bracket of rho with h will be equal to 0, right? Now in such a type of ensemble, okay, such a type of ensemble characterized by the density function rho equal to c somewhere in the relevant region and rho equal to 0 elsewhere, is corresponding ensemble is called the microcanonical ensemble. So the corresponding ensemble is called the microcanonical ensemble. Why? Because in the microcanonical ensemble we'll see that all the states, all the possible microstates are uniformly distributed. All the possible microstates are what? Uniformly distributed. So such an ensemble is what is known as what? Microcanonical ensemble. So this is the feature of microcanonical ensemble that you remember. So for a microcanonical ensemble, rho will be equal to a constant in the relevant region and rho will be equal to 0 outside. Okay. So now having concluded that rho will be equal to constant for a microcanonical ensemble, let's see what will be the ensemble average of any physical quantity f. So therefore ensemble average will be shortly calculating the ensemble average of various physical quantities like energy, the heat capacity, okay, see maybe the free energies, etc. Ensemble average of any physical quantity. Let me denote the general physical quantity as FQP. Okay, so in the microcanonical ensemble, where rho is a constant, what will be that? We have the definition of ensemble average, that is ensemble average is equal to, what is that equation? Hope you remember. We discussed the time average and ensemble average, where ensemble average is given by F integral FQP rho QPT, right? So it is to be weighted over or weighed over the density function d omega whole divided by the total number of members in the ensemble, that is nothing but integral rho QPT d omega. Now you know that in the case of microcanonical ensemble, rho is a constant. So rho is a constant. So if rho is a constant, you can take this rho outside the integral from both top and bottom, or in the numerator and denominator. So what will happen? That rho is taken out. So what remains in the numerator is integral f of qp d omega. Simply the integral of the quantity divided by rho can be taken outside here also, integral d omega. So that will be nothing but, you know, this rho and rho you can just cancel away, and integral of d omega in the denominator will give you omega. So it is nothing but equal to 1 by omega, where omega is the accessible or relevant region of the phase space. Okay, so integral f of qp d omega. So that will be the way in which see the ensemble average of a physical quantity f of qp will be modified in the case of a microcanonical ensemble. Okay, so that we have to keep in mind. So we have seen that a way in which the Poisson bracket of rho with h can vanish when the system is already in equilibrium is rho is independent of q and p. So let's see that in what other way see the Poisson bracket of rho with h can vanish. Okay, so the second condition, just let me go to, okay, yeah. So the second condition is that for rho h to be 0, so for the Poisson bracket of rho with h is equal to 0 if rho depends, it need not be constant, rho qp depends on q and p, not explicitly but implicitly. How? Through rho depends on q and p, not explicitly but implicitly, means rho depends on q and p through its dependence on h, which is the Hamiltonian of the system, and you know that h in general is a function of q and p, right? The Hamiltonian of the system. So this is yet another way in which the Poisson bracket of rho with h can vanish. That is, rho need not be depending on qp explicitly, but rho can depend upon qp through the dependence of rho on the Hamiltonian, which is in turn a function of what? Q and p. So let's see that how it is satisfied. That is let's prove it. Okay, that is rho a function of qp. I don't mean that it is explicitly a function of qp. That's equal to, through the dependence, rho is a function of h, where h is in turn a function of qp. So now what I'm writing is that rho is a function of h. That's all. Okay, rho is a function of h and h is a function of q and p. So we can say that rho implicitly depends on q and p through its dependence on the Hamiltonian, which is explicitly depending on q and p. Okay, so interdependence. Therefore, let's calculate. Therefore, what is rho h? We have to show that rho h is equal to 0 in this particular case also. Okay, rho h will be equal to, let's take it sum over I equal to 1 to n, of course, that is dou rho by dou qi into, the definition is dou h by dou pi, okay, minus dou rho by dou pi into dou h by dou qi. So that's the definition that I am rewriting. But you know that rho is a function of but rho is a function of h. Okay, in our case rho is a function of h. Therefore, okay, and h is a function of qp. So we have to just use the function rule in a partial derivative. Therefore, can you just modify rho h in the previous equation? That will be sum over I. How should I write dou rho by dou q? So I have to write first dou rho by, rho is a function of what? H. So I have to write dou rho by dou h into, then I have to write dou h by dou qi. So I have written this one replacing this particular parameter because of the functional dependence shown by these two things. So into what is the remaining? Dou h by dou pi into dou h by dou pi. So first two terms corresponds to the first term which I have I just circled in red, then minus. Similarly, dou rho by dou pi comes over here. How do you modify dou rho by dou pi here? So this dou rho by dou pi should once again be just replaced. How do you replace that? That is first dou rho with dou h, because rho is directly a function of h, which in turn depends on qp, into dou h by dou pi. Okay, into dou h by dou pi. Now that is the first term, into dou h by dou qi. Now look at the first term over here. So there are three partial derivatives being multiplied: dou rho by dou h by dou qa, dou h by dou pi. And what is the second term also here? That is the same thing, dou rho by dou h. Maybe the order is different, but in partial derivatives the order is immaterial. Dou rho by dou h into dou h by dou pi into dou rho. So means that both the terms are one and the same. So what is the result? The net result is that this case also we can see that you are getting the Poisson bracket rho with h is equal to 0. So what does it mean? So our conclusion is that the Poisson bracket of rho with h can be equal to 0 either when rho is independent of qp directly, means rho does not depend upon qp, or the value of rho is a constant in the relevant region of the phase space. In that case we can directly say that the Poisson bracket of rho with h will vanish. Certainly that is the simplest or straightforward case in which the Poisson bracket of rho with h will be equal to 0. But the thing is that for the Poisson bracket of rho with h to be equal to 0, it's not at all necessary that rho should be independent of qp. What other way it can satisfy? So it can be satisfied if rho is depending on q and p through its dependence on what? The Hamiltonian, which is in turn a function of what? Q and p, right? So the corresponding or the class of density functions, the class of such we can say that such density functions. So such density functions where rho depends on h, for which the corresponding ensemble is stationary. Therefore, such density functions for which the corresponding ensemble is stationary means dou rho by dou t is already equal to 0. So in that case, d rho by dt will be equal to 0. Means that the Lively's theorem is still obeyed. So remember that in general Lively's theorem is obeyed by all systems where there is a flow of representative points. It need not be a microcanonical ensemble where rho is equal to constant. It can be other ensembles as well. And so here we will be denoting one such choice, one such case where rho depends on h is rho qp proportional to, it's a function of e raised to exponential. I'm writing an exponential. e raised to minus h qp by kt. We will come across how this equation is coming and all we will be seeing later, but we are introducing it earlier. Okay, so I told you that rho is a function of h. So here there can be several ways of rho being a function of h. Rho can be say a linear function of h, rho can be an exponential function of h, rho can be a logarithmic function of h. Okay, so here we are taking one such case, one special case where rho is an exponential function of h. Okay, so the case is rho proportional to e raised to minus h by kt, where k is the Boltzmann constant and T is the absolute temperature. Or I can rewrite this one as rho equal to, simply avoiding the functional dependence and rho equal to, so the functionality can be okay just replaced with some constant rho 0. Okay, so into e raised to minus h by kt, rho equal to rho 0 into, so this is something that is quite relevant. We will be using this particular equation repeatedly later. So rho is equal to rho 0 into e raised to minus h by kt. So let me give some equation number 4, this one. So let me say that this is some equation number 3 or whatever it is. Okay, so now such an ensemble or an ensemble defined by rho given in equation 3 is known as a canonical ensemble. So we have seen two ensembles out of the three, the microcanonical and the canonical ensemble, and we have seen that the different kinds of ensembles are characterized by different functional form of density function. Our conclusion is that for a microcanonical ensemble, rho is independent of qp, means rho is equal to a constant in the relevant region of the phase space and rho is equal to what? 0 elsewhere. So any density function denoting a system in equilibrium which satisfies this condition is what is known as what? The microcanonical ensemble. And if the system is in equilibrium and a density function of the system is given by equation number 3 here, then such a type of an ensemble is known as what? Canonical ensemble. So we can say that a microcanonical ensemble and the canonical ensemble are having different types of density functions. Okay, or that is why I have just given the heading of this topic as density function for various ensembles. So density function for microcanonical ensemble and that for canonical ensemble are entirely different. Okay, so that is what we have to remember. Now let me just represent these two cases pictorially. That will help you to have a physical idea of what is the meaning of rho equal to constant, rho equal to 0 or rho equal to rho 0 into e raised to minus h by kt. So pictorially let's represent both the ensembles or density function. Density functions for both the ensembles can be represented pictorially. So here, for example, you consider the case of harmonic oscillator. Example, see, consider a harmonic oscillator, okay, having say that energy E, or you say the Hamiltonian is H. You know, for a conservative system, Hamiltonian represents what? The total energy. So you can either use H or you can use what? Total energy E. Now you know that it will be an ellipse. Okay, so as shown in the diagram here, it will be an ellipse. Now you know it's quite difficult to have a constant energy in practice. Usually the energy will be varying between some just say that some very small interval, right? So we'll say that hope you remember that we have been using that if the energy of the harmonic oscillator is having a spread of delta, okay, then we can say that the energy of the harmonic oscillator will be lying between E minus delta by 2 and what? E plus delta by 2. the energy of the harmonic oscillator, let us assume that it is lying between E minus delta by 2 and E plus delta by 2, where what is this delta? Delta is nothing but the spread in energy. You know that the Heisenberg's uncertainty principle limits, okay, that energy is what? Energy spread is 0. Okay, always there will be delta E into delta T should be having a finite value, right? So we cannot avoid, we cannot neglect what quantum mechanically the spread in energy. So instead of delta E, we have just used what delta. That's all. Okay, the symbol. So we can say that in the diagram. See, I have used just two elliptical trajectories here. So let's say that this particular thing is this particular trajectory. This corresponds for E minus delta by 2, and let the outer trajectory be corresponding to an energy E plus delta by 2. Hope you remember that the outer trajectories usually have greater energy compared to the inner trajectory. That was our analysis. Okay, so E plus delta by 2. So that what is the spread here? So what is the spread of energy here? So this spread will be equal to delta, the thickness. Okay, the thickness representing the spread of the energy here. Now in this means the harmonic oscillator will be having energy lying between these two see what you can say that energy shells, these two energy shells. Okay, so we can say that in this case the only accessible region of the phase space is what? The green colored space, which is between the two energy shells of energies E minus delta by 2 and E plus delta by 2. So what I am trying to do here is that I am trying to fill in the region between these two. Okay, so with some number of representative points. So I am taking care that not even a single representative point is just made outside this region. So, and moreover this the density of representative points, or the gap between density, in pictorially see the distribution of density representative points inside this particular shell region, energy shell region, should be uniform. So this is the meaning that rho is equal to constant. You can see that rho is equal to constant for which region? Between E minus delta by 2 and E plus delta by 2. So you can see that the density function, which denotes the number of representative points per unit volume of the phase space, that is equal to a constant here. So I have shown it to be constant. And what about the density function outside this particular shell? So for example, what is the density function here? Rho here is equal to 0. What is the density function here? Rho here is also equal to what? 0. So outside this particular shell, rho is equal to 0. So this is the meaning of stating that rho equal to a constant. Okay, where when the energy is lying between E minus delta by 2 less than or equal to H less than or equal to E plus delta by 2. So this is the way in which I am writing. Okay, and rho equal to 0 elsewhere. So you can see the density function, which is characterized by this particular property, is denoting what is known as a microcanonical ensemble. And why do you say that is a microcanonical ensemble? Because we can see that if you neglect the spread in energy, which is a consequence of the Heisenberg's uncertainty principle, we can treat the energy of the system to be a constant. Okay, energy of the system to be a constant. Therefore, the macro state of the system will be energy constant, volume constant, and number of particles constant. And you know, EVN ensemble is what is known as what? The microcanonical ensemble. So since energy is fixed, we say that the ensemble is a microcanonical ensemble. Now in the same manner, can you just imagine what will be the distribution of representative point for a canonical ensemble? What will be the distribution of representative points for a canonical ensemble? So for example, we are trying to draw the same phase space distribution for a canonical ensemble over here. So let's say that this is Q here and this is P here. We're just showing only 2 of the coordinates, where it can be 3n coordinates here and 3n coordinates there. So in order to understand the density function, the distribution of representative point for a canonical ensemble, we have to always recall what is its density function. And we have seen that the density function, unlike the case of unlike the case of microcanonical ensemble, where density function equal to constant somewhere and the density function equal to 0 elsewhere, here the density function is given by the exponential relationship. So that is rho equal to rho 0 into e raised to minus h divided by kt. What does it mean? It means that it's equal to, we can rewrite this one so that you can get a mathematical idea, rho 0 divided by e raised to h by kt. Is not the meaning? So we can take e raised to minus h by kt to the denominator. What does it mean? What is the physical meaning of this particular thing? It means that, it means that you say that the temperature at a particular fixed temperature, I'm taking a fixed temperature, okay, so I'm keeping a temperature constant. Then what will happen when the h increases, when the Hamiltonian increases? Hamiltonian represents the total energy. So when the total energy increases, what will happen? So you can see that when h increases, okay, so when h increases, I'm putting an upward arrow for increasing, okay, what will happen? E raised to h by kt will be getting increased. Means the numerator will be getting increased, and rho 0 is a constant, so the denominator is getting what? Increased, right? Okay, so e raised to h by kt term will be getting increased when h increases. So what will happen to the value of rho? The rho value will be getting what? Decreased. So that is a conclusion here. The rho will be getting decreased because rho 0 is a constant, right? And where do we have rho to have maximum value? So when h equal to 0, e raised to h by kt will be equal to e raised to 0, which is 1. So rho will be equal to rho 0. So maximum density will be there where the Hamiltonian h equal to 0. Or okay, we can say that when the Hamiltonian or the energy of the microstate is increased, the density function or the will be getting what? Decrease. So now how do you represent that one in the phase space diagram here? So we can see that I'm trying to represent the thing here. See, I think you just clearly understand that each of this is showing a representative point, and you know that the points close to 0, the origin of the thing, when at the origin means you know that both q and p are zeros, so the Hamiltonian is also what? 0. So we can say that here the representative point distribution will be like this. Just you have to go on comparing with that of the microcanonical ensemble. Now what happens as we can see, as you move away from the origin, you know that the energy will be decreasing. That's the meaning, okay? And you can just see that what I'm trying to do is I'm trying to show that the representative points are now, it may not be exactly clear, but even then I think I can just try to understand that what I'm trying to do. Okay, so now see that the representative points are now represented farther apart, and here the near to the origin the representative points are what? So crowded. Means when you move, okay, say that I'm taking a point over here, say that I'm taking a point here A, here let me say that the system is having a energy or Hamiltonian h1, and I'm taking a point here B where the system is supposed to have another Hamiltonian h2, okay, where the energy is different, okay. So therefore we can see that this particular, okay, whenever the system is having an energy h1, there the representative points, the density of representative point is what? More. And when system is having an energy h2, okay, where h2 is greater than h1, you can see that rho at h2 is less than rho at h1. Is not? That is, the density of representative points at the point B is less than the density of representative points at the point A. What does it mean? It means that the probability of finding that particular system with a lower energy H1 is more compared to finding that system with a higher energy H2. I repeat, okay, you know that representative points are denoting what? The accessible microstates, right? And more the number of representative points in a given region, it means that the more will be the chance that that particular microstates are what occupied. അല്ലേ? അപ്പോൾ ഇവിടെ നമ്മൾ പറഞ്ഞു വരുന്നത് ഇതാണ്, ഒരു സിസ്റ്റം ലോവർ എനർജിയിൽ കാണപ്പെടാനുള്ള സാധ്യതയാണ് ഹയർ എനർജിയിൽ കാണപ്പെടാനുള്ള സാധ്യതയേക്കാളും കൂടുതൽ എന്ന് ഈ ഒരു ഡെൻസിറ്റി ഫംഗ്ഷൻ വ്യക്തമാക്കി തരുന്നുണ്ട്. എന്തുകൊണ്ടാണ്? കാരണം നമ്മൾ കണ്ടു എ എന്ന് പറഞ്ഞ പോയിന്റിൽ ഡെൻസിറ്റി ഫംഗ്ഷൻ്റെ വാല്യൂ ഹൈ ആണ്, അല്ലേ? കാരണം അവിടെ റെപ്രസെൻറ്റേറ്റീവ് പോയിന്റ്സ് കൂടുതൽ ക്രൗഡഡ് ആണ്. ആൻഡ് വെൻ യു മൂവ് ടു ദ പോയിന്റ് ബി, ദ റെപ്രസെൻറ്റേറ്റീവ് പോയിന്റ്സ് ആർ നോട്ട് സോ ക്രൗഡഡ്, ദേ ആർ ഫാർദർ അപ്പാർട്ട്. എന്താ അതിൻ്റെ അർത്ഥം? ഈച്ച് ഓഫ് ദ റെപ്രസെൻറ്റേറ്റീവ് പോയിന്റ് ഈസ് റെപ്രസെൻറ്റിംഗ് ആൻ ആക്സസിബിൾ മൈക്രോസ്റ്റേറ്റ്. പക്ഷേ അധികം മൈക്രോസ്റ്റേറ്റുകളൊന്നും ആക്സസിബിൾ അല്ല ആ റീജിയനിൽ. അതിൻ്റെ അർത്ഥം എന്താണ്? സിസ്റ്റം ആ പർട്ടിക്കുലർ ഹൈ എനർജിയിൽ കാണപ്പെടാനുള്ള സാധ്യത താരതമ്യേന എന്താണ്? ആ ലോ എനർജിയിൽ കാണപ്പെടാനുള്ള സാധ്യതയെക്കാളും എന്താണ്? കുറവാണ്. ആൻഡ് യു തിങ്ക് ഓഫ് ഫിസിക്കലി, ഇതല്ലയോ നമുക്കറിയാവുന്നത്? ഡോണ്ട് യു നോ ദ ബേസിക് ഐഡിയ ദാറ്റ് എവറി സിസ്റ്റം in order to achieve equilibrium will try to reduce its energy എന്ന് നമ്മൾ പണ്ട് തൊട്ടേ പഠിച്ചു വരുന്നതാണ്. So it's a very basic underlying concept. Okay, every system tries to reduce its energy in order to achieve what? Equilibrium. നമ്മൾ ഓൾറെഡി പറഞ്ഞു കഴിഞ്ഞിരുന്നു. ഓക്കെ, എന്താണ്? ഈ രണ്ട് സിസ്റ്റത്തെയും നമ്മൾ ഇക്വിലിബ്രിയത്തിലാണ് എന്നുള്ള അസംഷനിൽ, ഡോ റോ ബൈ ഡോ ടി ഈക്വൽ ടു 0 എന്നുള്ള അസംഷനിൽ എടുത്തിട്ടാണ് നമ്മൾ എന്ത് ചെയ്തത്? റോ ഈക്വൽ ടു കോൺസ്റ്റന്റ് എന്നോ അല്ലെ റോ ഈക്വൽ ടു റോ 0 ഇൻ ഡി റേസ് ടു മൈനസ് എച്ച് ബൈ കെ ടി എന്നൊക്കെ എടുത്തത്. അപ്പോൾ അതിൻ്റെ അർത്ഥം, if a system is in equilibrium, okay, right, the probability of that system to be found in a lower energy state is much higher compared to the probability of finding that same system in a higher energy state. ഇനി നിങ്ങൾ ഒരു പക്ഷേ നിങ്ങൾ ശ്രദ്ധിക്കേണ്ട ഒരു കാര്യം ഇതാണ്, ഇവിടെ നമ്മൾ എഴുതിയിരുന്നു റോ ഈക്വൽ ടു റോ 0 ഇ റേസ് ടു മൈനസ് എച്ച് ബൈ കെ ടി. എച്ച് എന്നുള്ളതിന് പകരം ഞാൻ ഇ എന്ന് വിളിക്കുകയാണ്, ബിക്കോസ് ഫോർ എ കൺസർവേറ്റീവ് സിസ്റ്റം എച്ച് വിൽ ബി ഈക്വൽ ടു ഇ, ദ ടോട്ടൽ എനർജി. ആൻഡ് ഐ ഹോപ്പ് ദാറ്റ് യു ആർ വെരി ഫെമിലിയർ വിത്ത് ദിസ് പർട്ടിക്കുലർ ടേം. You have seen this particular term many a times when you are using what you call the distribution functions for Fermi, Dirac, Bose-Einstein, etc. You have been writing this e raised to minus e by kt, or maybe I think you remember that the same expression e raised to minus e by kt you would have seen when you are studying about the population of states at a particular temperature and how the population varies, especially when you study about lasers, or when you study about what in spectroscopy you are studying that n by n0 is equal to e raised to minus, right, e raised to minus e by kt, right, or n is equal to n0 e raised to minus e by kt. The number of particles in the upper state and the number of particles in the lower state are connected. And how come this particular factor, ഈ ഫാക്ടർക്ക് എവിടെ നിന്ന് വരുന്നു എന്നുള്ള കാര്യം അന്വേഷിച്ചാൽ ഇതിൻ്റെ എല്ലാം തുടക്കമാണ് ഞാനിപ്പോൾ പറഞ്ഞു വരുന്നത്. ബിക്കോസ് all these concepts are obtained from statistical mechanical considerations by the concept of what? Ensemble theory. Okay, so just as a conclusion, this is what I want to tell you, that the density functions are different for different ensembles. Each class of ensemble can be classified or characterized by a class of density functions. And if density function equal to constant in a given region and it's equal to 0 elsewhere, then that represents an ensemble with the energy remaining constant with a permitting a spread of delta, where delta is very small. Okay, and such an ensemble is microcanonical ensemble. And if the density function is exponentially decreasing with the Hamilton of the system, then such a density function can represent what is known as what? Canonical ensemble. And you know that in canonical ensemble, okay, so that is okay, why do we say that this is a canonical ensemble? The reason is that in canonical ensemble we permit energy to vary. E is varying. That's why I have taken H1 here, means E1 here and E2 here. The system can exchange energy with the surrounding, because the canonical ensemble represents what? Not an isolated system but a closed system where energy can be exchanged. So E can change. But what is remaining constant? So as I told you here, the temperature of the system is supposed to be what? A constant. So we can see that this is what is known as an NVT ensemble. So in place of energy, E, the energy is varying. Okay, energy is varying, whereas what? The temperature is treated to be a constant. So such a type of an ensemble which represents what? A closed system is known as a canonical ensemble. Okay, so that's all regarding the two kinds of ensemble and their corresponding density functions. Okay, thank you.